So this is lecture number 2 of grammar. So first lecture we saw the basics of grammar. In the second lecture we will see Chomsky hierarchy. Now let's see. The Chomsky hierarchy was described first by Noam Chomsky in 1956. It classifies the grammars based on the forms of their production ruler. The Chomsky hierarchy also classifies languages based on the classes of grammars generating them. The formal definition is provided below. So grammar G is a quadruple, that means it is a 4-tuple. G equal to V, T, P, S, where V is a finite set of meta symbols or variables, or we say non-terminal symbols. T is a finite set of terminal symbols. P is a finite set of production rules. And S belongs to V is a distinguished element of V called the start symbol. So your S is the start symbol, and the start symbol belongs to V. That is finite set of non-terminal symbols. So a production rule is a form X belongs to Y. So what is production rule? Production rule is in the form of X belongs to Y, where X is a member of a set of strings composed of any mixture of variables and terminal symbols, but X is not the empty string. So X can never be an empty string. Y can be empty. So it can be A is like this, it can be. So that means you can replace A with a epsilon string, a empty string. But A can never be empty. So basically X can never be empty. This side, that is your non-terminal will never be an empty string, will never be an empty string. But whatever is there for Y, in place of Y, whatever you have, you can be keeping an empty string is allowed. So Y is a member of set of strings composed of any mixture of variables and terminal symbols. Y is allowed to be an empty string. So type 0 grammar. So first we'll learn about the type 0 grammar. How many types are there? Type 0, type 1, type 2 and type 3. In Chomsky we have 4 types. So first we'll learn about the type 0 grammar. That is your unrestricted grammar. Type 0 grammar generate recursively enumerable languages. They generate the languages that are recognized by a Turing machine. So what kind of languages they are generating? They are generating the languages which are recognized by a Turing machine. And what kind of language is accepted? Recursively enumerable language is accepted. Language accepted, and they generate languages that are recognized by a Turing machine. A language is recursively enumerable if there exists a Turing machine that accepts every string of language and does not accept strings that are not in the language. So it will accept every string of the language and will not accept the strings that are not present in the language. So strings that are not in the language may be rejected or may cause the Turing machine to go into an infinite loop. So either they will get rejected or they will be again and again checked. So again and again it will be going in an infinite loop. In type 0 grammar, the productions have no restrictions. They are any phase structure grammar, including all formal grammars. The productions can be in the form of alpha will be to beta. So you can say where alpha is a string of terminals and non-terminals with at least one non-terminal. So alpha should have at least one non-terminal, and alpha can never be null. That means epsilon you will never use for alpha. Epsilon not allowed. Empty string not allowed. Beta is a string of terminals and non-terminals. For beta, epsilon is allowed. For alpha, epsilon is not allowed. Now, example, let's see. You have been given E. You have E is your non-terminal, and you can replace that with capital ACAB, which is a mixture of terminal and non-terminal. BC, this is again a mixture of terminal and non-terminal containing at least one non-terminal. So B is your non-terminal. ACB, mixture of terminal and non-terminal. CB, both of them are non-terminal. DB, again both of them are non-terminal. AD, terminal, non-terminal, but it is containing at least one non-terminal. You have DB. DB is a mixture of terminal and non-terminal. Example 2 is SABBA. Again, you have this is your non-terminal. AS, this both are your non-terminals. So, in your left hand side, that is this part, LHS, suppose I say, and this is your RHS. So, we say that at the LHS, you need at least one non-terminal. So your variables are SA and terminals are AB. So actually it is not called LHS or RHS. It is just for your understanding. I have kept that notations. So variables are SA and terminals are AB. Example 3, consider a grammar. So let's see this grammar. They have been given some grammar. The following are the derivations in the grammar. Let's see the derivations. S, they say that S is $CA hash. Now what I am doing, I am replacing C with AAC. So I replace C with AAC, C. If I replace C with AAC, I get this, and this hash will be written as it is. In the next step, I will replace C hash with E. So replace C hash with E. What do I get? $AAE. Now in the next step, I will replace AE. So replace AE with EA. When I do that, I get AEA. A as it is written, and you get AEA. Now, in the next step, I will again replace AE with EA. So, this first AE, you replace it with EA, and this A written as it is. Now, in the next step, I will replace $E with a null string, that is epsilon. So, this will become 0. What will I get? I will just get AA. So, I hope this is clear. How is the replacement done? It's very simple to understand. There is nothing so complicated. Now, let's see the next example. Next example is a little bit bigger. So, let's see this. First, you have this string. Now, for this, how will I do? How can I proceed? I will replace CA with AAC. So, replace CA with AAC. So dollar will come as it is, even your, so symbols will come as it is. CA will be replaced by AAC. Now, after this, I will replace C hash with D hash. So you replace C hash with D hash, AA will come as it is. After that, I will replace AD with DA, AD with DA. So you replace AD with DA, A will come as it is, even hash will come as it is. Now, in the next step, I will replace again AD with DA. When I do this, I get DA, A written as it is, hash written as it is. So this beginning AD I am replacing with dA. So A and hash will be written as it is. Now what will I do? I will replace, what can I replace now? I will replace $D with $C. So this $D will become $C and AA hash as it is. Next, I will replace CA with AAC. CA replaced with AAC. So CA you replace with AAC and A hash and dollar will be as it is. Next, what will I do? Next, I will replace again I will replace CA with AAC. When you replace the CA, you get AAC and AA as it is. Next, I will replace what? I will replace C hash with capital E. So instead of C hash, I will write capital E and all the A's will be written as it is. Next, I will replace AE with EA. So replace this AE with EA. Next, I will again replace AE with EA. So what do I get? When I replace AE with EA, I get here EA and 3 A's will be written as it is. Again, I will replace AE with EA. So AE, this AE replace it with EA. This A as it is, this A as it is, this A as it is. Again, I will replace AE with EA. So I will get this AE. If you replace, you get EA. Now I will replace $E with epsilon. $E with epsilon. What will I get? I will get 4 A's. So now L of G, that is the language, is nothing but A raised to I such that I is a power of 2 is your conclusion. So I hope this is clear. Now type 1 grammar is called as context sensitive grammar. Type 0 we have done. Now type 1. Type 1 grammars generate context sensitive languages. So what kind of languages they generate? They generate context sensitive languages. So we say that the language which is accepted by this type is context sensitive language. The production must be in the form of alpha A beta will be alpha gamma beta, where A belongs to N non-terminal and A comma B comma gamma belongs to T union N asterisk strings of terminals and non-terminals. The strings alpha and beta may be empty but gamma must be non-empty. The rules: S is, you can replace S with epsilon, is allowed if F does not appear on the right side of any rule. The languages generated by these grammars are recognized by a linear bounded automata. So in the type 1 we saw it was Turing machine. Over here it is linear bounded automaton. In type 1 grammar production in the form of alpha is replaced with beta, where alpha should be less than equal to beta, that is count of symbol in alpha is less than or equal to beta. Now let's see an example. Consider the following. This is your example. Let's see how to solve this. So first they have said that S is nothing but belongs to nothing but small a, capital A, B and C. So I will change this part, capital A and B. So non-terminal always you have to change. So if I do this, capital AB, convert it to BA. So I get BA, A and C written as it is. Now I have to change AC because again this is non-terminal. AC changes to capital B, small b, C, C. So capital B, small b, C, C, A, B as it is. Now small b, capital B changes to capital B, small b. So capital B, small b, capital B changes to capital B, small b, and A will be written as it is and B, C, C will be written as it is. Next, what will be done? AB will be changed to AAA. So you have to replace it with AAA. So AB changes to AA. Small a, capital A, and this part BBCC written as it is. Next, I will change AB to BA. So this AB changes to BA, 2 A's written as it is, BCC written as it is. Next I will change AB, change to AB, change to BA. Again this AB will be changed to BA, CC written as it is, AAB written as it is up. Next, what will I do? I will change AC to BCC. So AC changes to BBCC. This last C written as it is and AABB written as it is up. Next, what will I do? I will change small b, capital B to capital B, small b. So small b, capital B, small b, BCC written as it is, and this part is written as it is up. Okay, next you will change what? Again small b, capital B change to capital B, small b. So you get what? You get A, capital B, small b changed to B, 1, 2, 3, 4, 5. Now, next what will I do? I have to get rid of this B. So, because this is non-terminal. So again, what will I do? I will change. What will I change? I will change this AB to AA. When I change this AB to AA, what do I get? AAA. Change this AB to AA. Otherwise, everything will be written as it is. So I get 3 A's followed by 3 B's followed by 3 C's. So what is the conclusion? The language generated by this grammar is A raised to N, B raised to N, C raised to N. N should be greater than equal to 1. And you are getting here 3. So A raised to 3, B raised to 3, C raised to 3. So this was all about type 1 grammar. Now let's see type 2 grammar, that is a context-free grammar. Type 2 grammars generate context-free languages. The productions must be in the form of alpha will be replaced, A will be replaced by beta, where A belongs to N non-terminal and beta belongs to T union N asterisk string of terminals and non-terminals. Left hand side of the production can have only one variable. There is no restriction on beta. These languages generated by these grammars can be recognized by a non-deterministic push-down automata. So type 0 recognized by Turing machine, type 1 recognized by linear bounded automata, type 2 recognized by NFDA, non-deterministic finite PDA, push down automata. So NFPDA, non-deterministic finite push down automata. Let's see, the example is S will be XA, X will be replaced by A, X will be replaced by A and capital X will be replaced by A, B, C, and capital X will be replaced by a empty or a null string. So this is also, it is called as a empty string, or you can also call it as a epsilon string or epsilon. For example, S will be replaced by A, capital A will be replaced by small a, capital B will be replaced by small b. Next is your type 3 grammar. Okay, that is your regular grammar. So this is your last type in your Chomsky hierarchy. Type 3 grammars generate regular languages. Type 3 grammars must have a single non-terminal on the left hand side and a right hand side consisting of a single non-terminal or a single terminal followed by a single non-terminal. So in the left hand side only one single non-terminal should be present, and in the right hand side it consists of a single terminal or a single non-terminal followed by a single non-terminal. So it can be A or A. Single terminal followed by a single non-terminal or a single of a single terminal or a single terminal followed by a single non-terminal. So single terminal followed by a single non-terminal, or it can be just a single terminal. The rule production X is epsilon is allowed if X does not appear on the right side of any ruler. Type 3 is most restricted form of grammar. So example is what? X belongs to epsilon. X is A or capital A, small a, capital Y. Y is replaced by small b. So for example, summation is A comma B is equal to S. P is your production, is a regular grammar and it generates all strings consisting of A's and B's including the empty string. The scope of each type of grammar. This is a very important diagram which says the scope of each type of grammar. So we will summarize the whole thing. Chomsky classification of grammar. The following table shows how they differ from each other. Type 0 grammar, grammar accepted, unrestricted grammar, language accepted, recursively enumerable language, automaton, Turing machine. Type 1 context sensitive grammar, language accepted, context sensitive language, automaton, linear bounded automaton. Type 2 grammar accepted, context free grammar, language accepted, context free language, automaton, push down automaton. Type 3 grammar accepted, regular grammar, language accepted, regular language, and automaton is finite state automaton.